Hey everyone, hope you're having a good day. Today we're going to have a little intro to solving trig equations. And we've solved some things like this before, but this is going to be just a little bit more in-depth, and it goes well with the identities stuff because it meshes well with the manipulation of trig functions and variables. So let's take a look and see what we can figure out. So first we'll start with where we've been. What we've been doing is we've been proving what are called identities. Got green today for St. Patrick's Day. So we got identities. Identities. Okay, and identities are things that are always true. So to prove this, this is one of the Pythagorean identities that we've been taking kind of for granted to be true, but I'm just going to show the proof, right? We do sine squared over cosine squared x. Plus 1, I'm going to change the 1 to a cosine squared x. Well, gosh, giving away my answers. Cosine squared x over cosine squared x. All over the place. There we go. And that is equal to sine squared x plus cosine squared x over cosine squared x. Top is 1. That's a Pythagorean identity. So that's 1 over cosine squared x, which is secant squared x. Okay, and that ends our proof. Now, this is what's called an identity. It is always true for all values of x. No matter what x you choose, the left side is equal to the right side. We just proved it by using just ideas of reciprocal identities and also Pythagorean identities. And these are always true for any value of x. So where we're going now is we've seen some equations that are not true for every value of x. In fact, most of the equations that we have, we are trying to solve for a particular value of x. For example, if we have something like 2x plus 1 equals 5. Okay, is this true for every value of x? No, right? If you plug in like 7 for x, this is not true. So what do you have to do? You have to solve for x, right? So 2x equals 4, x is 2. Okay. So there's particular values for x that you have to solve for. Now what we're going to do today is we're just going to throw in trig with this. So instead of seeing like x's here, we might put in like a sine x or a cosine x, and we have to solve out using that trig function. So this is kind of the easiest that trig problems get, where you're given a variable and you have to solve for it. So how we would have done this back in chapter 4 is you guys probably would have taken sine inverse of both sides, and you would have said, well, sine inverse is only good on the right side of the circle, so we have to get something over here where it's 1/2, and you would say it's pi over 6, right? But the problem is, what we're going to do now is we're going to actually get to a general solution for this, because think about the sine wave, right? Sine wave looks like this. Goes in both directions. Forever, right? Like that. So now they're asking, when is sine equal to 1/2? Well, 1/2 is like right here. It's halfway up to the top of the wave. So they want to know, when does that dotted line intersect with the sine wave? Well, how many times does that happen? A lot, right? Like an infinite number of times. And that's why we had to restrict the range for the sine inverse function to just values on the right side of the circle. Because we said we only wanted one. Now, I want them all. I want you to give me a way to tell every single spot on the sine wave where that dotted line intersects the sine curve. And that sounds kind of daunting at first, but it's really not too bad. And most problems are broken down like this. So they say, first, give me all the x's between 0 and 2 pi where this is true, and then we're going to find a general solution. Excuse me. So, between 0 and 2 pi, that sounds like it'd be good to draw a circle. So when is sine 1/2? Well, there are two spots that happens. It happens over here at pi over 6. Happens over here at 5 pi over 6. Those are the two spots where we have the short value for sine, right? So our short little vertical distance right there. Those are the two spots that we get between 0 and 2 pi, and that's all you have to do. So pi over 6 and 5 pi over 6. And then the general solution, so what we just found here, this is 0, this is 2 pi, right? That's one full period. So what we just found was this guy right here, that's our pi over 6. And this guy right here, that's our 5 pi over 6, right? So that's on the x-axis down here. Those are the two x values that make the sine curve equal 1/2. Now let's think about how we can get to the next one. All right, so let's look at the positive value only. So I'm just going to focus on the pi over 6 for a second. So I'll take away my 5 pi over 6. I'm going to say, when do I get to the next time I'm going uphill and I intersect with 1/2? Well, think to yourself for a second, what should that distance be? I'm going from the exact same point on the sine curve to the exact same point on the sine curve again. That's one full period. So I've gone by 2 pi. Now I could actually find that value, but what I'm going to do is I'm going to say, well, that's pi over 6 plus 2 pi. Now, if I continue this, when is the next one going to happen? When I'm going uphill. That'll happen in an additional 2 pi. So I could write that as pi over 6 plus 2 times 2 pi. And the next one would be 4 times 2 pi. Or sorry, 3 times 2 pi, and then 4 times 2 pi. So every 2 pi, I'm going to get that uphill solution. The way I write that is pi over 6 plus 2 pi n. And n is an integer. You don't have to write that. It's kind of assumed, right? Or sometimes people write n is an element of the integers. So that crazy e means element of. Remember, we talked about that z. It's German for to count, I believe, which is Zahlen. It might be numbers. I don't remember. It's German. And so this n means that it could be 1 or 2 or 3 or 4 or any number, as long as it's something in the integer. So it's what you guys would probably call a whole number. Also, it could be negative, right? I couldn't get this value right here, because that would be when n is -1. I would get back to here, and then -2 would get me further left, and -3 would get me all of the ones when I go uphill. How do I get the downhills? Well, that brings me back to the idea of 5 pi over 6. When do I get the next one? Well, it's 2 pi later, right, over here. So pi over 6 plus 2 pi n, also 5 pi over 6 plus 2 pi n. So all you do is add the period, and that would be the solution I'd be looking for. Because this is telling me every time that you hit something that's a multiple of 2 pi beyond pi over 6, that you're going to be at 1/2. That's all you have to do. So this is kind of the next level. We have 2 cosine x plus 1 equals 0. Very similar to the last problem, except this time what I want to do is I want to make it look like this. So I want to isolate that cosine. So to isolate the cosine, I'll subtract 1 from both sides. So I'll have 2 cosine x is equal to -1. Then just divide by 2. So I have cosine x equals -1/2. Okay, so once you have that cosine isolated, now we're just going to think about the circle. So between 0 and 2 pi, where are we -1/2? Well, that's the short horizontal value, so that happens here and also down here. That's 2 pi over 3. You might need to review your unit circle if you haven't looked in a while. Down here, that's 4 pi over 3. So those are our 0 to 2 pi's, 2 pi over 3, and then 4 pi over 3. Now the general solution, this is even easier than it was last time. I have my two values. So if you think about the cosine wave, you can if you want to. You never have to draw this if you don't want to. -1/2 is right here. My question is, when do I intersect? This was our 2 pi over 3. This was our 4 pi over 3. Next time you're going to hit those values are 2 pi later. So we just add the period to both of these. So it's going to be 2 pi over 3 plus 2 pi n and 4 pi over 3 plus 4 pi n. Sorry, 2 pi n. And again, the reason you need both of those, I get that question a lot. Why can't you just do one of them? Because the distance between them is not 2 pi. You have like the downhill one and the uphill one, and that's going to happen every time. You're going to have a downhill and an uphill. So you have to do 2 pi between every period for the downhills and 2 pi between every period for the uphills. That's really all there is to it, though. So let's take a look at something just a little bit different. What about tangent? So tangent, what is different with tangent and sine and cosine? Think about the graphs. Graph of tangent looks like this. Swoops up like that, got an asymptote. Way different than sine and cosine. But what happens is, if I want to make it equal to something, so let's solve this out for tan x. So if we do, I'll put that somewhere else. So if we solve this, I would have tan x equals 3 over root 3. And we could rationalize root 3 over root 3. So I get tan x is equal to 3 root 3 over 3. The 3's cancel, so I have tan x is equal to root 3. Now you guys are probably thinking about the circle, and if you think about the circle, there's a couple spots where tan is root 3. It happens up here at pi over 3. That's when our tangent value is long, right? And also down here at 4 pi over 3. But think about the graph. Root 3 is a number. It's like up here somewhere. If this is 1, root 3 is just a little bit more. If I draw my line, notice that unlike sine and cosine, where we like had an uphill and a downhill answer, here we just have the one answer, and it happens every period. But what's the period of tangent? Hopefully you know that that's pi. So we get our answer here, and what they might ask you to do is just give an answer between 0 and pi, because you get all tangent values between 0 and pi, and then they just repeat themselves. So you're going to hit it every pi. So you really only need one answer on the top. So between 0 and pi, that happens up there at pi over 3. That's when tan is root 3. Between 0 and 2 pi, well, it's pi over 3 and 4 pi over 3, but those are exactly pi apart from each other. You really only need one solution because there's no like uphill and downhill like we had with cosine and with sine, right? Because you had to hit those two, because within a period you could hit two different ones. With tangent, we only get the one that it comes from on each swoosh. So really all you need is the pi over 3. And then you add the period, which for tangent is pi n. The other option is you could write pi over 3 plus 2 pi n and 4 pi over 3 plus 2 pi n. But that seems like a little bit more work than you need. So the easier way to think about it, I think, is just when you see tangent, find the one solution from 0 to pi, and then add pi n. So I'm actually going to erase this since we don't need it. That's all there is to solving equations with tangent in them. Cotangent, same idea, right? It's just pi. Sine, cosine, secant, cosecant have a period of 2 pi. Tangent and cotangent have a period of pi. So, one more concept that's going to be important for solving those problems on your gold sheet is when you have 0, you want to use it to your advantage. So think about a problem like this. If you have like, okay, making up problems in my head, always dangerous. Let's say we have x squared minus x plus 6 equals 0. Okay, and this is actually getting a little bit more into what we're going to do on Friday, doing a little bit different type of problem. But you could factor this. Looks like x minus 3, x plus 2 equals 0. So your solutions to this would be x equals 3 and x equals negative 2, right? Because we're multiplying two things together and it equals 0. That's the zero product property, which you may have learned at some point in your mathematical career. Zero product property tells us that when you're multiplying two things together and it equals 0, that can only happen if one of them is 0. So either x minus 3 is 0, so x is 3, or x plus 2 is 0, so x is negative 2. Same thing over here. If sine x times cosine x is 0, then one of them has got to be 0. So either sine x is 0 or cosine x is 0. Well, sine x is 0 at two spots on the circle, right here and right here. Cosine x is 0 at the top and the bottom. So I'm at one of the compass points. So either I'm at 0, pi over 2, pi, or 3 pi over 2. You can write 2 pi, but that's kind of redundant for the 0. And then for each one of those, I have to add the period. So plus 2 pi n, plus 2 pi n, plus 2 pi n, and plus 2 pi n. So this time we got 4 solutions. That's it. Now, some people, it's tempting to, like, at the beginning here, say, well, I'm going to divide by cosine. Don't do that. Because if you divide both sides by cosine, you lose a solution. In fact, you lose two solutions. You would lose the pi over 2 and the 3 pi over 2. You have more solutions if you use the 0 to your advantage. Right? So that's why I wrote that up there. If you have sine and cosine together, either one then can be 0. So you end up with more possible solutions, which is kind of cool. So, a little bit different flavor here. Cosine cubed over sine is equal to cotangent. So I'm going to put everything in sines and cosine. So this would say solve for x, something like that. So it's easy to get this confused with an identity, but this is not an identity. This is not always true. Cotangent is cosine over sine. So saying that that's equal to cosine cubed over sine, that's just not true, right? Because the sines would cancel. You'd have cosine cubed equals cosine, which is not an identity. So this is only going to work for certain values of x. Now, first thing I'm going to do is I'm going to multiply both sides by sine. That's going to cancel these out. Now, that's okay. It's okay to get rid of those because when you have a sign on the bottom, it's not going to make this solvable. It's not going to help me solve, so there's no 0. It's not like I am losing a solution. But now I have cosine cubed x equals cosine x. This is where you could lose a solution. If you divide both sides by cosine, you're going to lose out. What I want to do is I want to subtract cosine from both sides. So I have cosine cubed x minus cosine x equal to 0. So you get it equal to 0, and now we're going to see if we can factor something. These share a cosine in common. So I do cosine times cosine squared minus 1 equal to 0. So one of those two things has to be 0. Either cosine is 0 or cosine squared minus 1 equals 0. And at this point, you gotta have a couple choices. You could see this as kind of like a Pythagorean. It's close, but it's negative. So you could change that to cosine x times negative sine squared x. I'm actually going to just set each of these equal to 0. If you do this, it'll give you the same solutions. You can try that as an exercise if you want to. But here, I either have cosine equals 0, or I could have cosine squared minus 1 equals 0. That's an or. Cosine x equals 0, that happens at pi over 2 plus 2 pi n, and 3 pi over 2 plus 2 pi n. Cosine squared minus 1 equals 0. Well, if I add 1 to both sides, I have cosine squared x equals 1. So that means when I take the square root, that cosine x could be positive or negative 1. Remember, when we take the square root, we get two solutions. Cosine x is plus or minus 1 at 0 and pi. So we're going to have 0 plus 2 pi n, and also pi plus 2 pi n. 2 pi n, there we go. All right, and those are our four solutions. If you had done this, sine is 0 at 0 and pi, so you would end up with the same solutions. I think I have one more. Might have two more. We'll see. So I have 2 sine x cosine x equals sine x. So I'm going to do pretty much the same thing as last time. I'm going to subtract the sine from both sides. So I have 2 sine x cosine x minus sine x. Tempting to divide, but don't do it. Equal to 0. Factor out a sine, so I'll have sine x times 2 cosine x minus 1 equals 0. Don't forget the 1, right? You can't lose that sign. So now we have either sine x equals 0 or 2 cosine x minus 1 equals 0. Well, sine is 0 at 0 and pi. So we could have 0 plus 2 pi n and pi plus 2 pi n. Those are for sure solutions. Over here, if we solve this, add 1, divide by 2, we get cosine x equals 1/2. That happens at pi over 3 and 5 pi over 3. So we have, no, let's do pi over 3 first. So we have pi over 3 plus 2 pi n and 5 pi over 3 plus 2 pi n. So, 4 solutions. Any one of those will make this true. It's not an identity. Only works for these 4, let's call it a family of solutions, because it's not really just 4 solutions. There's an infinite number of solutions, because we have this 2 pi n thing going on. But you have a lot of solutions out there that are at specific points on the curves that will make this true. Yep, one more. So this guy, we got 4 cosine squared x equals 1. Going to solve this, divide by 4. So we have cosine squared x equal to 1/4. Now take the square root, and remember, when we take the square root, how many solutions do we get? We get 2. So we have cosine x could be plus or minus square root of 1/4, which is plus or minus 1/2. So cosine x could be positive or negative 1/2. 4 spots where that happens. It's all of like the hourglass points. All the pi over 3s. So we have pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. We just have to add 2 pi into each one. Pi over 3 plus 2 pi n. 2 pi over 3 plus 2 pi n. 4 pi over 3 plus 2 pi n. And 5 pi over 3 plus 2 pi n. And those are our solutions. So really just finding the spots on the circle. So isolate, find the spots on the circle, throw in a 2 pi n, or if it's tangent or cotangent, a pi n. And that's all you have to do. So, homework, keep plugging away on the yellow packet. I know some people have been struggling with that a little bit. Keep trying it. Just use those formulas that we came up with the other day for the sum and difference formulas and the double angle formulas. Check out the gold sheet now. You should be able to do that using this new knowledge of solving some trig equations. On Friday, I'm going to be looking for progress on both of those, and then we'll also be learning something new on Friday, and then we'll have work and question time after that. If you have any questions, as always, you can send me an email or come see me before or after school. I would love to chat with you about math. Nothing makes me happier. Love you guys. That's why I'm here. Have a great day, and I will see you soon. Bye-bye.